Having seen increasing summations and decreasing summations, there are two other things to be wary of. In particular, if a summation is geometric, it's a number to the I, or if somewhere in it a number to the I shows up, you need to be slightly wary about what's going on. Here we have a summation that has a number to the I in the denominator there. We need to be careful about how we analyze this. We're going to analyze this with a formula first, and then try to also analyze it by bounding and see how they compare and contrast in terms of both the difficulty and in terms of how they work mathematically. So let's try and analyze this using our formulas. We have t of n is equal to the sum from I equals 0 to log base 2 of n. You may rightfully hesitate for a second and say, wait a second, log base 2 of n is not an integer very often. We could include something like a floor function around this to round it down, or a ceiling function to round it up. However, those things are rarely going to matter, so for our purposes, we'll just assume that that's an integer and sweep under the rug the fact that a lot of the time it's not. Of n squared divided by 2 to the I. We want to try to exploit our formula that says that if we have r to the I, we know what it is. So let's try and do the algebra required to do that. We factor out the n squared, then have the sum from I equals 0 to log base 2 of n of 1 divided by 2 to the I. Why did I factor out the n squared? In order to use the formula as we have written it, we need to have strictly a number to the I inside of the summation. Can we rewrite this? Notice we have a 1 in the numerator. We can actually write that as 1 to the I, because 1 to any value is 1. Therefore, we can now exploit a useful algebra trick to rewrite this as the sum from I equals 0 to log 2 of n of 1/2 to the I. And now we have munged it around in such a way we can now use our formula, which is a number to the I. So let's off to the side remind us what the hell was that formula. That was we have the sum from I equals 0 to n of 1 of r to the I. It's equal to 1 minus r to the n plus 1 divided by 1 minus r. We have that exact format over here, with n being played by log base 2 of n and r being played by 1/2. So let's use this formula. This is equal to, using that formula now, n squared times 1 minus 1/2 to the top bound, log base 2 of n plus 1 divided by 1 minus 1/2. Now we have an algebra problem to try to simplify this. 1 minus 1/2 in the denominator is not so bad, and we can also do some arithmetic in the numerator. We have 1 minus, I'm going to write the numerator as 1/2 to the log base 2 of n times 1/2 divided by 1 minus 1/2 is 1/2. Dividing by 1/2 is the same as multiplying by 2, so this is 2n squared times quantity. I now need to deal with the logs and the exponents, and not great, but we'll see what we can do. This is 1 minus 1/2 times, I can use the property where I can take the exponent of both the numerator and the denominator separately. Exponents work very well with multiplication and division. This is 1 to the log 2 of n, which is just 1, divided by 2 to the log base 2 of n. We can now simplify as 2n squared times quantity 1 minus 1/2 times 1 divided by 2 to the log base 2 of n is just n. I can now distribute that 2n squared and get 2n squared minus a bunch of stuff cancels in the second term, and we just have n. We would now need to bound this above and below by a number times n squared, because this looks like it's in theta of n squared. So we can bound this above by dropping the n squared, and we can bound it below by replacing the n with an n squared, and be left with n squared, and that's only true so long as minus n is greater than or equal to negative n squared. Divide by negative n, and we have 1 less than or equal to n, or n greater than or equal to 1. So somewhere in here I need to say n is greater than or equal to 1. So it's bounded above by 2n squared and bounded below by 1n squared. So it is in theta of n squared. So t of n is in O of n squared, and t of n is in omega of n squared. Thus, t of n is in theta of n squared. All of that seems well and good. Notice that algebra here gets a bit messy, and these were nice numbers. I consciously chose them to work out nice. This can become a bit of a nightmare. So one advantage that our bounding technique we were using has is that it avoids some of the ugly constants that show up sometimes. In particular, it avoids them by just kind of replacing them with nicer looking numbers. This one might not have been so bad, but maybe we can try to bound this and see what happens. Let us start with the summation we were given. T of n is equal to the sum from I equals 0 to log base 2 of n squared divided by 2 to the I. Now we need to try to bound this above and below. First question you need to ask yourself, as we've seen in our previous two examples of bounding, is you need to know whether or not the summation is increasing in I or decreasing in I. As you plug in bigger and bigger values of I, this gets divided by bigger and bigger powers of 2. Therefore, it is a decreasing function of I. Alternatively, you could write out the terms of the summation to determine this. The first term of the summation is n squared divided by 2 to the 0, that's 1. Plus n squared divided by 2 to the 1, that's 2. Plus n squared divided by 2 to the 2. Plus n squared divided by 2 to the 3, and so on and so on and so on. Clearly, those terms are getting smaller. You're dividing by bigger and bigger numbers. So in either case, you identify that it's decreasing. And if we try to bound this above, let's use our technique we used. To bound it above, we bound it above by the biggest term in the summation. So this is less than or equal to the sum from I equals 0 to log base 2 of n. And we replace I with the smallest value because it's decreasing to make it as big as possible. We replace I with the smallest value within the range. So this is less than or equal to the same thing, but plugging in I equals 0. This is equal to the sum from I equals 0 to log base 2 of n squared, which is equal to the number of terms, log base 2 of n plus 1, times the inside, which is n squared. And I did that a little fast. Remember, we had removed the I, therefore we simply take the inside, which no longer has the summation index appearing inside of it, and multiply it by the number of terms in the summation, which is the top bound minus the bottom bound plus 1. Notice, we haven't finished bounding this, but we can identify a problem that's occurring, which is this looks like n squared log n, which is not the complexity. We showed already it was in theta of n squared. Therefore, our upper bound was too big. Ooh, now, it's not great, right? Something weird is going on here. What happened? The reason is geometric things decrease so quickly that this technique actually makes it too big by replacing them all with the biggest term. So instead of doing this, which does not work now, so don't try this, let's try a different technique. So to bound this above instead, what we're going to do is keep everything exactly the same, I equals 0, and keep the inside n squared divided by 2 to the I, but we're going to change the top bound to infinity, which seems like utter insanity to do. But it's going to turn out to be a fantastic idea. Now, let's try and use our infinite geometric series formula that we mentioned before. This is equal to, I'm going to factor out the n squared, then we have the sum from I equals 0 to infinity of 1 divided by 2 to the I. Just as we saw before, we can write this as 1 to the I, because 1 to any power is 1. So it's equal to n squared times the sum from I equals 0 to infinity of 1/2 to the I. And now we have a formula for an infinite geometric series. Remember, in our list of formulas we had the sum from I equals 0 to infinity of r to the I is equal to 1 over 1 minus r, so long as absolute value of r is less than 1. So this is equal to n squared times, I'm going to use that formula, r is being played by 1/2, this is called the common ratio, 1 over 1 minus the common ratio, which is r, and this is equal to 1 divided by 1/2, which is the same as 2n squared. We did the exact algebra before. So it's bounded above by 2n squared. Hold on. If we notice, that's exactly the upper bound we had here. And we didn't have to fiddle around with any stupid log rules to do that. And we didn't need to do a bunch of algebra. all we had to do was write it as a number to the I, then replace it with an infinite geometric series. And it turns out that this technique will work for any decreasing geometric sum that we encounter. So, we bounded it above by 2n squared. How on earth are we going to bound it below by a constant times n squared? This is actually even easier than this. If I go back to the terms of my summation, it looked like n squared plus a bunch of garbage. So clearly, if I stop writing all of these additional terms and just drop them entirely and just keep the n squared, the first thing in the summation, that is clearly going to be a number times n squared. It's 1 times n squared. So this is greater than or equal to the original summation, going from 0 to log base 2 of n squared divided by 2 to the I, is definitely bigger than or equal to n squared, because we're dropping every term except the first. And that always holds. We don't need to say any caveats about n. We don't even need to think about what we're doing. We're just dropping all of the other terms except for the first term in the summation. Therefore, it is bounded above by a constant times n squared and bounded below by a constant times n squared. Thus, the exact same reasoning we said above can be copied. So we're going to take the exact conclusion we drew and paste it down here. We did the exact same thing. We bounded it above by a constant times n squared and bounded it below by a constant times n squared. In fact, we bounded it above and below by the exact same constant times n squared as we did before. And notice, there was really no rules to do here other than trying to figure out how to write it as a number to the I, which was already required anyway. This technique is oftentimes superior to using the formula that we tried to use before, because the math almost universally works out better this way. However, it is equally valid to do either of these techniques. I personally prefer this bounding technique because it involves fewer steps and is usually less prone to errors.